Hi, turkeys. Today I'm going to show you these notes about mass extinctions. And this is what you're going to fill out while you do this. You probably pick these up on the way in. And then you might want to have this out, maybe both of them out, just because they're always good to refer to. I have them out every time I look at any of this stuff. Okay. All right, let's begin. Okay, so mass extinction is defined as a time where species vanish faster than they are replaced. Okay, um, so we have a time frame for that, 2.5 to 3 million years, and 75% or more of the world's species are lost during that time. So um, a lot of scientists right now are saying that we are in um, the beginnings of another mass extinction. Um, we are on our way up, like our species that are becoming extinct. Um, they're moving up, and if they continue moving like this, um, for 2.5 to 3 million years, then this will be another mass extinction. It hasn't really happened yet. We're kind of in the beginning of that 2.5 million years. Okay. All right. So we have 5 big ones. Okay. So there have been 5, and then the 6th one, if you hear someone talking about the 6th one, it would be the one that we're in right now. Okay, so it hasn't completely happened yet. So there have been 5 mass extinctions. And this graph is pretty cool because it talks about this extinction rate. And this one is talking about families per million years. And I know that you guys remember, like you can kind of see right here. These are some words that y'all probably remember from biology, I hope. Species, uh, genus, families. So that's how they're defining this. Like if and a certain number of families go extinct. So like if we get above this line, I believe, so 10 families per million years, which it's a lot. It doesn't sound like that much, but it is a lot. So let's see. Down here, let me move my cute little face. We have this is coming up. I'm not sure when this was made, but it is coming up. You know, we have a huge population of humans, and we have to live somewhere. So we are, getting rid of a lot of environments where animals live. That's a big part of it. And also, when we cut down all those plants to do this, we also cut down on all those plants that are sucking in carbon dioxide. And so I know that you guys know all of that. We will talk about that again later, but that's why we're on our way up here. Okay. Okay. So we've had 5 according to this time scale. Most scientists agree that we're in the midst of one right now, or at the beginning of one, really. I should change that to in the beginning of one. We are rapidly approaching a loss of diversity similar to that seen during a mass extinction. So we haven't gotten there yet, but we are on our way. So the first one that we have is this Ordovician. So it's the end of the Ordovician and the beginning of the Silurian. And when you see them, a lot of them are on boundaries like this because this is the defining event. Like that is why there's a Triassic and a Jurassic, not just one big time period. These are big events that shape our time scale. Okay. Okay, so chronologically, the very first one was at the Ordovician-Silurian boundary in the Paleozoic. And so this is the oldest one, or the first one, and it was 440 million years ago. Okay. It was possibly caused by an ice age causing glaciation. So that would be climate change. And then rapid warming period. Again, that is climate change. And it says anoxic oceans, which means that the oxygen has been somehow removed from the oceans. And that is actually kind of happening right now, too. I know that you guys have heard about like the coral reefs disappearing. That it's part of that. So, an estimated 85% of marine species were lost. This was a really big mass extinction, and it brought in a decline of reef ecosystems. So, most of us, or most animals, let's see, during the Ordovician, we had mostly invertebrates there, and so we most things were in the water, and so we saw a decline of these reef ecosystems, and we saw a diversification of fish with jaws, with bony jaws. Okay. The second one was at the end of the Devonian. This was 375 million years ago. And this one, we do have some evidence that there were asteroid impacts, volcanic eruptions, and sea level fluctuations. Okay. An estimated 80% of marine species were lost. And this is kind of pretty similar to the same. So, widespread reef destruction and a decline of diverse marine life. So, of course, we still do have diverse marine life in the oceans now, but not like we did before this Devonian mass extinction. The third one is at the boundary of the Permian and the Triassic, so 252 million years ago. This one is also caused by volcanic eruptions, so global warming and climate change, and ocean acidification. The ocean became anoxic, so the oxygen came out of the oceans, and so the things with gills could not breathe in the oceans because there wasn't oxygen in there. And we also had widespread desertification, so we had deserts being formed at that time. An estimated 96% of marine species and 70% of land vertebrates were lost, which is, this number is crazy. 96%. I mean, it's amazing that we still have anything left after that, right? And then this was a really devastating impact on all life forms. And this mass extinction really paved the way for the rise of the reptiles. So if you look at your black and white time scale and you look at the end of the Devonian, so before that we had amphibians, right? So we had animals that could live on land, but then after that mass extinction, we got rid of a lot of land vertebrates, so maybe a lot of predators, and so animals were safer on land, and so that paved the way for reptiles to come in and kind of dominate. Okay, and then we have the fourth one, was at the boundary of the Triassic and the Jurassic. This is 201 million years ago. And again, this is volcanic eruptions. This is the one, oh no, actually that's not. I was going to say this was the dinosaur one, but it is not. Volcanic eruptions, asteroid impacts, and climate change. So when we have volcanic eruptions, we have a whole lot of black smoke blocking out the sun and really changing the amount of light that comes through. It changes the amount of photosynthesis that can happen. Asteroid impacts are kind of the same way. It shoots up so much stuff. Like think about when we talked about Thea, it shoots up so much vaporized rock that it makes like a smog kind of, but a really, really bad smog. Okay, so that does change our climate a lot. This says we lost 76% of marine animals and some land vertebrates. We used to have giant amphibians. I hope that you guys see those in the game that you play today. I saw them when I played the game, but it probably depends on like what you pick. But the giant land amphibians were lost. You know, we have little amphibians like salamanders and frogs and stuff, but they're pretty cool. And then the significant impact is, excuse me, that this opened the door for dinosaurs to kind of take over and have their big heyday. So if you look on your on your black and white chart, let's see. At this time, we did have mammals, we did have dinosaurs, but they weren't like the big dominant thing, and they weren't super diverse either. So we had early dinosaurs and early mammals. Then, when we had this mass extinction at the end of the Triassic, then the dinosaurs really became like the dominant life form. And you can see on your chart it says age of dinosaurs. Okay. The fifth one is at the boundary of the Cretaceous and the Paleogene, which was only 66 million years ago. So just take a look at your chart, okay? And I mean, it was, you look at the millions of years, woo, it wasn't that far away, right? And this is one that people talk a lot about. They call it the KT extinction event. And I looked this up because they used to always call it that in college, and I can never really remember why. But the K is for Cretaceous. I don't know why they have it with a K. But the T is for the tertiary. And if we actually look back, if we look back here, is it on here? It's not on here. So if you look at this one, at this chart, okay, if you look at this does have the tertiary. It's in the Cenozoic, okay? And so it's the period after the Triassic, Jurassic, and Cretaceous. All right. It has been split up into a lot of things. So it's not on every chart as the tertiary. Okay. And on this chart, it's kind of Cretaceous and Paleogene, right? So this one, we know why this happened. This is the big one that happened that made all the dinosaurs go extinct. A large asteroid impact, and we don't even know where it was. It was in the Yucatan Peninsula, which is really close to where we live, right? It led to widespread wildfires, global cooling, and tsunamis. So this created like these wildfires, and then the asteroid impact, it made all that vaporized rock. So it made like a nuclear winter kind of situation, which again, it blocks out the sun. Plants can't do photosynthesis. So a lot of things died. An estimated 76% of all species, including non-avian dinosaurs. So the flying dinosaurs, they stuck around. They were able to make it through this, and they became birds. Pretty cool. So this got rid of the dinosaurs, and then mammals came in, and they became the dominant land vertebrate. Humans would not be here if not for this. This is when we had a lot of the megafauna, is after this mass extinction, where we had like the giant armadillos and the giant sloth. This is where we got mastodons and elephants. So we had a lot of megafauna here, okay, starting because of this. It didn't come until later, okay? All right. So one thing that I always wonder is how do we know that any of this happened? Right? We're just letting people tell us this stuff, but there is evidence of it. Okay. That we know that there was an ice age in the southern hemisphere at the time of the first mass extinction down after the Ordovician. And it would have cooled the global climate. And we know this from glacial deposits in the Sahara Desert. So we can actually see the evidence of these glaciers in the Sahara Desert. Okay. For the one after at the end of the Devonian, we probably know the least amount about that one. Mostly we just see a lot of things disappear from the fossil record. So the Devonian is just the last time that we see any of that. Triassic and Jurassic, we see, I don't really understand this, but there's a major compositional shift in a carbon isotope. So they can tell the difference between like the carbon that existed before and the carbon that existed after. So they can tell the difference in the sediments. And then the Triassic, that sediment is almost like it doesn't have any fossils in it because there weren't a whole lot of things left after that. Okay. And then the KT boundary, no dinosaurs have ever been found in sediments that were deposited after the tertiary. So that is crazy, but that makes perfect sense, right? We can't find any in the sediments if the sediment is older than the tertiary because that's when they all died. Kind of crazy. That's all. I hope that this wasn't too doom and gloom, but it's all things that happened in the last 4.5 billion years.